10. N. All right, so let us begin again. So this is what we did last time, right? So we have okay, so we have started solving, right? So it is error analysis. Right, so this is called error analysis. And so what we did is this, right? So we solve system AX equal to B, right, by using right. So we solve the system AX equal to B by using iteration method, which is given by xk plus 1 is equal to mxk plus c, right? So that is how we solve the system. So now what we are going to do is you know that, right? Right, so this is what we do after doing the computation by using the iterative method. What we do is we approximate the real solution x by one of our computed value xk, right? So that xk can be any computed value depending on how long you iterate and how long you iterate according to the equation. So that is how we usually do the approximation when we apply iterative method. So obviously, you know, there should be a difference between the real value and the computed value because we take this as an approximated value. So obviously there should be an error. So right, so the difference between the real value and the approximated value is given is known as the error in the approximation. Right, so you have you know that this is the error in the approximation. So now the point is we want to estimate the error, right? In real numerical computation, you all know that you cannot compute the error, right? So if you can compute the error, then obviously you know it is uh, it is easy to compute the real value rather than computing the error, right? So obviously you know you cannot calculate the error. So you try to estimate the error here, right? So so we try to find the error bound here, right? So basically what we are going to do is we want to find, right? So first this is obvious for all of you, right? Right, so this is something you already know, right? By the way you create the equation, you write x is equal to mx plus c, but the iteration is xk plus 1 is equal to mxk plus c. So when you subtract one from the other, you get this, right? So you get x is equal to xk plus 1 minus x is equal to this. So what you do is you take the norm on both sides, like the length, the size of those vectors. Right, so when you take the size, right, so norm of the vectors, you get xk plus 1 minus x is less or equal to norm of m times norm of xk minus x, right? So what you do is, but again, you see that when you are doing a real numerical computation, you don't know the real solution also, right? Because if you know the real solution, then there is no need for the numerical computation at all. So when you are doing a numerical computation, on actually you don't have the real solution. So in this case, this is the error, right, at the k plus first step. But this is again an error. So you don't have, you have unknown values on the both sides of the inequality. So this inequality does not help you to get the error bar, right? So in this case, what you are going to do is you can do this. So you take this is less or equal to norm of m and norm of xk minus norm of xk plus 1 plus xk plus 1 minus x. So in this inequality, what you do is you add and subtract an xk plus 1 inside the norm. So in this way, there is no change, right? So you add and subtract the same value, which you can always do, and that does not change the values of the computation. So now what you do is you apply the triangle inequality. So when you apply the triangle inequality, you know that this becomes okay. So when you apply the triangle inequality to this is less or equal to norm of xk minus xk plus 1 and then plus norm of xk plus 1 minus x. So eventually what you get is norm of xk plus 1 x is less than or equal to this. Right. So here you can solve this inequality for norm of xk plus 1 minus x. So once you solve this, you will end up with norm of xk plus 1 minus x is less or equal to norm of m over 1 minus norm of m norm of xk minus xk plus 1. Okay, so if you solve the inequality for norm of xk plus 1 minus x, you get this, right? So this is what you have. So here you can easily see that this one is the error in the approximation, right? By approximating xk plus 1 as the approximated solution x, right? So the error there. And this bound is basically norm of m minus 1 over 1 minus m, right? So this is true, and this one is the difference, the size of the vector, right? Xk minus xk plus 1, right? So the distance between the two successive iterations. Right, so this inequality is true as long as 1 minus norm of m is positive. So clearly m should be less than 1. Then only 1 minus m is positive. Then only you can divide by 1 minus m on both sides and you don't get the inequality flipped the other way around. Right, so that's how you do the computation. So this is called the error bound. Right? Right, so this term on the right hand side of the inequality is known as the error bound, right, in the approximation, right? So when you approximate x k plus 1 as the approximation for x. So here M is the iterative matrix. So you know different types of iterative matrix for Gauss-Seidel method, Jacobi method, and successive over relaxation method, right? So you can always verify those or change the iterative matrix according to the method we are using and derive the error bound accordingly. So this is how we do the problem. So what I am going to do now is I am going to give you an example, and I will do it for Jacobi method, and you can do the same for other methods as well, right? So I am going to do the approximation, and then I am going to find the error bound as well, right? So this is how I'm going to do. So let me write the exercise. First I will give you a system of equations. So that is 4, 0, 1, 1, 0, 4, 0, 1, 0, 0, 1, 0, 0, 4. Okay, so consider a system like this: 4, 0, 1, 1, 0, 4, 0, 1, 1, 0, 4, 0, 1, 1, 0, 4, x1, x2, x3, and the right hand side vector is 1, 2, 3, 4, right? So let me write down what we have to do first. First part is by using the initial value 0, 0, 0, 0, you apply the Gauss-Seidel and Jacobi iterations, right? Second, Okay, so there are 4 parts in this question, but even within every part you have sub parts, and so you have to do a lot of work in this exercise. So given the system of linear equations, right, what you have to do is you have to get okay, so you have to apply Jacobi method first. Also you have to apply Gauss-Seidel method, right? And then what you do is, assuming that you approximate x2 or the real solution x by the second iteration x2, right? By assuming that x2 is considered as the approximation for the real solution in both Jacobi iteration and Gauss-Seidel iteration, right? So in both cases, they ask you to determine the error bound, right? So you have a formula for error bound, right? They ask you to determine the error bound, right? So right, so they will give you what kind of norm you can use, right? So here, let us say we use infinity norm, right? So that is maximum norm. In the matrix, it is a maximum row sum norm. And then they ask you to do all the things for an SOR method with omega, because whenever you are using an SOR method, an omega should be given. So in this case, they give you omega is equal to 1.01. The fourth part of the question is, will these iterations converge? So will the sequence generated by those iterations converge? And you have to justify your answer, right? So if you give answer as yes, then you have to say why you say yes, or even if you say no, then again you have to say why you say no, right? So that is why what I mean by justify. Right? So whatever the answer, either yes or no, you have to provide a valid mathematical reason for your answer. And so these are the 4 parts in this question. So what I am going to do is I am going to do the question for Jacobi iteration only. Right? So I will do part 1, part 2, and part 4 for Jacobi iteration for this example, and leaving the Gauss-Seidel and SOR method as an exercise for you to do as a homework. So obviously, whenever you have a system of linear equations, and if you want to solve it by iterative method, then you have to see it first, to make sure that you have to split the matrix A into I minus L minus U, right? So in order to do that, you have to divide everything by 4, right? So first step is this. You have 1, 0, 0.25 and 0.25, right? 0, 1, 0, 0.25, 0.25, 0, 1, 0, and then 0.25, 0.25, 0, 1. So if you divide each row by 4, right, because 4 is the diagonal term, so you have to make sure you have 1 on the diagonal first. Then you divide each row by 4. When you divide the first row by 4, you get this. Second row, third row, fourth row. All rows are divided by 4. So 1 divided by 4, you can keep it as 1/4, or you can write it as 0.25. And 3/4, I can write it as 0.75. 2/4, I can write it as 0.5. So this is my A and C now, right? So I can write L and U now. Okay, so these are going to be your L and U, right? So when you write this A as I minus L minus U, L is this, U is this, and C is that, right? So then you know your Jacobi iteration, right? Jacobi iteration is this. Right, so the Jacobi iteration is xk plus 1 is equal to L plus U times xk plus C. Right, so that is your Jacobi iteration. So you apply this with x naught, right? So when you put k is equal to naught, right, you will get x1, right? So here, because x naught is all 0, right, eventually x1 is C. Right, so x1 is C, that is clear, because you can just do the computation and get this x1, right? So this is your Jacobi iteration. Right? And then what you do is you get the second step in Jacobi iteration. So that you may need to do some calculation. Right, so x1, so when you put x2, k is equal to 2, when you put k is equal to 2, you get x2, right? That is equal to L plus U of x1 plus C, right? So that is the Jacobi iteration. So you can substitute the matrix. I am not going to write the matrix again and show you the substitution, because you know how the substitution works, right? So then L plus U multiplied by x1, which is 0.25, 0.5, 0.75, and 1, right? And then you add with C, that is again 0.25, 0.5, and so on. So when you do that, let me write the answer directly, and you check of your own by doing the work again, right? And see whether the answers are right or wrong. So please make sure that you double check the work, because this might be not correct, right? So you just rework everything and double check the work. It is just matrix multiplication and addition, so that's not a big thing. You can try it, right? So now this is how you find x2, right? And then you go to the second part, right, where they ask you to find the error bound, right? So you know that the error bound second part is this: x2 minus x is basically, they ask you to use the infinity norm, is norm of m minus 1 minus norm of m, right? So here your m is L plus U, you know that. Right, so they ask you to find the error bound. So in the error bound formula, you substitute for xk plus 1 as x2, right? And then xk plus k is x1, right? So then you have this, right? So L plus U is the iterative matrix. So L plus U infinity norm divided by 1 minus norm of L plus U infinity norm. times x2 minus x1. Okay, so you have to find all these things, right? So you have to find L plus U infinity norm, right? And then x2 minus x1 infinity norm, right? So because I already have L and U here, let me find out the infinity norm of L plus U. Right, so this is infinity norm of L plus U is the maximum of row sums, right? L and U when you add it together, right? And then you take the sum of the row terms, right? For each row, absolute value of each terms in the each rows, right? And then you take the maximum. So you get maximum of, I will say, row sum, right? Absolute row sum. Right, so that is the infinity norm of L plus U. So you will get the maximum of each of the rows. Right, so first row L plus U, there is 0.25, 0.25, so 0.5. So let me write down 0.25 minus of 0.25 absolute value plus minus of 0.25 absolute value. And second row, there is only one minus of 0.25 absolute value. Third row, right, 0, 0, 0, and there is only one minus of 0.25. And then fourth row, there are minus 0.25, minus 0.25, and all the others are 0. So it's the sum of 2 minus 0.25 absolute values. Right, so among these numbers, you pick the maximum. So it is 0.5, 0.25, 0.25, and 0.5 again. And so you have four numbers and you pick the maximum, so that is clearly 0.5. Okay, so you find the infinity norm of the matrix L plus U, that is 0.5. Now you have to find the infinity norm of x2 minus x1. So you have x2 here, you have x1 here, so you subtract one from the other and then you take the maximum of among the absolute value of the components. And so you subtract, right, so x2 minus x1 or x1 minus x2, whatever way you can do. Right, so this 0.25 plus 1.875 minus 0.25. Okay, so you can subtract x2 and x1, right? If this x2 is correct, then you can subtract x2 minus x1, right? So then you have these values, and then for the infinity norm again, this time it is a vector. So infinity norm is maximum among absolute value of the component. Right, so infinity norm is the maximum among the absolute value of each of the components. So you can take the absolute value and take the maximum. Right, so that is obvious here 0.4375, 0.75, 0.0625, and 0.1875. So in this case, clearly it is 0.75. Right, so that should be the maximum among these numbers. Okay, so now what you can do is you can substitute in the error bound and obtain the error bound. Right? So infinity norm of L plus U, that is 0.5. One minus infinity norm of L plus 2, that is 1 minus 0.5, and then infinity norm of this is 0.75. Okay, so this is so this is 0.7. So that's basically 0.7. Okay, so here the error bound is 0.75 when you approximate x2 as the approximation for the original solution x. Right, so this is how you determine error bound. So here it is Jacobi iteration. So I use L plus U as the iterative matrix. And for other matrices, Gauss Seidel and SOR method, you may need to use the corresponding iterative matrix for the error bound. Right. So now the fourth part, third part is applying the SOR method, which you can do similarly, similar to what I did here for Jacobi, right? The only difference is the iterative matrix is different. So once you do Gauss Seidel, then Gauss Seidel, you all know it's a special case of SOR, so it's almost similar. Right. So now what we have to do is we have to do the part 4, which is asking about the convergence of the method. Right. So part 4, the question is, will these iterations converge? Right. So we have to do for all the iterative methods. So let's do it for Jacobi. Right, so we know Jacobi iteration converges. Because if you look at the theorem we do for Jacobi iteration with diagonally dominant matrix, right? Okay, so in 4 rows of A, you can see that the diagonal term is 4, and off diagonal terms are 1, 1, 0. Right? On the first row, 2 of the off diagonal terms are 1 and other one is 0, so it's going to be 1 plus 1 plus 0. That's 2 is obviously strictly less than 4. And in the second row, you can see that 0, 4, 0, 1. So the off diagonal term summation is 1, diagonal is 4. So that row is again diagonal term is larger. Same for third row and same for fourth row. So eventually you can see that in all 4 rows, diagonal term dominates the off diagonal term, sum of the off diagonal term. So clearly A is strictly diagonally dominant. when we talk about the convergence of the Jacobi method in theory, we show that we do a theorem which says if the coefficient matrix A is strictly diagonally dominant, then the Jacobi method converges. So here clearly you have A is strictly diagonally dominant, therefore you can say that the Jacobi method converges. So this is one way of answering the question, right? So one way of answering the question is you observe that A is strictly diagonally dominant and you show that because of that the Jacobi iteration converges. There is an alternative way also, right? Without using the fact that A is strictly diagonally dominant, you can still show the convergence. So this you have, right? Right, so infinity norm, you have norm of xk plus 1 minus x infinity is less or equal to m times, which is L plus u, xk minus x infinity, right? So this is the standard way of writing the iteration, right, minus the formula, right? So the system Ax equal to b, right? So in this case, you can see that by continuing this, right, so I did this in theorem as well. Right, so when you continue doing this, right, xk minus x is less than or equal to L plus u infinity times xk minus 1 minus infinity. So it's L plus u quantity squared times xk minus 2 minus infinity. And when you continue doing this, you will get this, right? So xk plus 1 minus x infinity norm is less or equal to L plus u k infinity norm to the power k plus 1 times x to the x naught minus x, right? But you already know L plus u infinity norm is 0.75, right? So we just computed it, right? The L plus u infinity norm is 5. Right? So if we just computed it, it is 0.5. That is strictly less than 1. Right? 0.5 is obviously strictly less than 1. Right? So if that is less than 1, so L plus u infinity norm to the power k plus 1 will converge to 0 as k goes to infinity, right? Because the L plus u infinity norm is strictly less than 1. So if the term is less than 1, because you know if it is 1 upon 2, 0.5 is 1 upon 2, when you put 1 upon 2 to the power n power and n goes to infinity will goes to 0. You all know that. If that goes to 0, then xk minus 1. So then clearly the xk plus 1 will convert to x as k goes to infinity. So that also guarantees the convergence. So there are two ways to justify the convergence of Jacobi method. Here one is directly by using the theorem which we studied earlier, and we can show that the matrix A is strictly diagonally dominant, because if it is strictly diagonally dominant, the sequence will converge. Or because you computed the infinity norm of L plus u already, you can use that and directly show that the iterative method converges by using the fact that norm of L plus U for infinity norm is strictly less than 1. Right? So these are the two ways to do that. And by using a similar approach, you can do the same thing for the other iterative methods as well. So we will stop here with this, and in the next class what we are going to do is we are going to do the error analysis in general for the computation of the solution of the system Ax equal to b. Right? So we will talk about that in the next class.